My name is Emma Frank, your mathematics tutor. In this package, we are going to look at matrices. Before we start, let's look at the behavioral objectives. At the end of this teaching, the students should be able to define a matrix. The students should be able to state types of matrices. The students should be able to perform algebra of matrices. These are the objectives. Let us take the definition of matrix. An array of real or complex numbers arranged in rows and columns in a rectangular form is called matrix. Matrix is denoted by capital letter, while its elements are denoted by lowercase letters, that is small letters, enclosed with large brackets. Example: A equal A11, A12, A13, till I have A1n. A21, A22, A23, A2n. And then we have A31, A32, A33, A3n. And this continues. We have AM1, AM2, AM3 till AMN. Now this is example of matrix. Yes, where Aij denotes the elements in the ith row and jth column. Yes, so for any Aij, denotes the element in the ith row, the j column. For I equal 1, 2, 3, m. Then we have j equal 1, 2, 3 till n. Right. So that if I say A11, for instance, mention A11, it means elements in row 1, because this is called rows. This is row, while this side is column. This one is column, and that's why we say that an array of real or complex numbers arranged in rows and column in a rectangular form. You can see that this thing resembles rectangle. It is called matrix when you arrange it in that way. Matrix is denoted by capital letter A. It can be another letter, but here, what we know generally, matrix is denoted by capital letter, while its elements are small letters. So A11 means elements in row 1, column 1. Now notice this. If I write A32, it means elements in row 3, column 2. This is the elements. But this is row 3. This is column 2. Now here is column 1, column 2, column 3, till we have column n. Now A32 means elements in row 3, column 2. If I say A33, elements in row 3, column 3. Now notice that we first mention the row before the column, so that if I write like this, A42, it means elements in row 4. So you first mention row 4, column 2. Good. Thus, a matrix is said to be of order n times n. Now the order of the matrix is given by this. Where m is the row and then n is the column, so that the matrix 2 by 3, if I write 2 by 3, means that there is a matrix, say A, in which it has 2 rows, for instance, 2, 3, 1, 5, 6, and -1. So this is 2 by 3. 2 rows. Let's mention the row. This is a row. This is a row. So 2 rows and 3 columns. Now the first one denotes the row. Then this is column. Also, 4 by 3 matrix will mean that we have a matrix, say B, whose rows are 4 and the column is 3. So we'll have something like this. Maybe -4, 1, 0, 2, -3, 5, 6, 2, 1, 8, 9, -7. So this is 4 by 3 matrix. The row is 4. That's 4 rows, and the column 3. So that is how matrices are arranged. Now let's look at types of matrices. We'll look at types of matrices. The first one we'll look at is what we call square matrix. A matrix is called square matrix if it has equal rows and columns. So a matrix is called square matrix if it has equal rows and columns. For example, matrix A equal 4 to 1 minus 9 is a square matrix. So it has 2 rows and 2 columns. Matrix B 3 4 1 8 6 2 5 1 3 it's a square matrix because it has 3 rows and 3 columns. So that's square matrix. Another type we want to look at is what we call null matrix. Now let A denote a matrix A is called null matrix if all its elements are zeros. Example, matrix A is a null matrix. Have another one, matrix P. It's a null matrix. Okay, and let's look at another type that we call identity matrix. Let A denote a matrix A is called an identity matrix if all its elements are zeros except the elements in the principal diagonal which are all unity. Example, okay, let us do this, that identity matrix is denoted by I. So example, we have I equal 1 0 0 0 1 0. So this is identity matrix. Now notice that the whole element here are zeros except the principal diagonal. This is the diagonal element, and they are all unity. Unity means 1. They are 1 1. All true. They are 1 1. So this is identity matrix. You can also have it in this way: 1 0 0 1. This is also identity matrix. Alright, let's go to other types. Next one is diagonal matrix. Let A denote a matrix A is called a diagonal matrix if all its elements are zeros except the principal diagonal elements. Example, if I have like this, A11, A22, A subscript 33. This is a diagonal matrix. Notice that in diagonal matrix, the diagonal element, the principal diagonal element, must not be in unity, so that this matrix A 3 0 0 0 minus 4 0 0 0 7 is a diagonal matrix because it has elements only in the principal diagonal. So that is a diagonal matrix. Next one we'll look at what we call triangular matrix. Let A denote a matrix A is called a triangular matrix if Aij equals 0 whenever I is greater than j. For I equal 1, 2, 3 till m, j equal 1, 2, 3 till n. In other words, A is called a triangular matrix. In other words, okay, let A denote a matrix. A is called an upper triangular matrix. An upper. Then in triangular matrix, we have what we call upper triangular matrix and lower triangular matrix. So here I'm defining upper triangular matrix. So A is called an upper triangular matrix if Aij equals 0 whenever I is greater than j. For I starts from 1 to n. J is 1 to n. I start from 1 to n. In other words, A is called an upper triangular matrix if all its elements below the principal diagonal are 0. Example, I have something like this: A11, A12, A13, A22, A23, A substitute 33. This is an upper triangular matrix. You can see that this arrangement resembles a triangle. So we call this upper triangular matrix. All the elements below the principal diagonal are 0. Okay. Now let us look at lower triangular. If A denotes a matrix, then A will be called a lower triangular matrix if A I J equals 0. Whenever I is less than j. Now I equal 1, 2, 3 till m, and then j equal 1, 2, 3 till n. In other words, a matrix whose elements above the principal diagonal are all zeros are called lower triangular matrix. Example, if I have A as a matrix and I have A11, 0, 0, A21, A22, A2, A31, A32, and A substitute 33. Then this is a lower triangular matrix. But that's lower triangular matrix. All the elements above the principal diagonals are 0. Now why do we define it this way? Now look at, for any aij equals 0. aij equals 0 whenever I is greater than j. That is for upper. How? Now look at here. This is row 2. I stand for row. So here is column 1, row 2. Row 2, column 1. So 2 is greater than 1. That place becomes 0. Row 3, column 1. 3 is greater than 1. Becomes 0. Row 3, column 2. 3 is greater than 2. So it's 0. And that is now what I'm trying to define. Here is the same. Whenever I is less than j, it becomes 0. So in simplicity, what it means is that this is a lower triangular matrix if all the elements above the principal diagonals are 0. So that is a lower matrix. Now the next one is transpose of a matrix. Transpose of a matrix. Let B be a square matrix. The transpose of B, denoted by B raised to the power T, is the matrix whose column are the rows of B. In other words, the transpose of matrix B is another matrix which rows of B are transformed to become the column of the B transpose. For example, let A equal 3, 4, 1, 6, 2, 5, minus 2, 0, and 1. Okay, minus 1. This is a matrix. Now let us find the transpose of A, denoted by this. It is a matrix whose row of this A, the first, that row there, will carry the row and turn it like this to become a column. So this row now, if you carry it and turn it to be a column, you have 3, 4, 1. If we go for this row, we carry the row and turn it to be column, we have 6, 2, 5. Then here is the row. We will turn it, we turn column to have minus 2, 0, minus 1. Now this is transpose of this. Okay. Now the next one we'll look at is what we call symmetric matrix. Symmetric matrix. Let A be a matrix if A equal A transpose, then if A equal A transpose, then matrix A is called symmetric. Symmetric matrix. For example, look at this matrix. A equal this matrix A. Now I want to take the transpose which is given by this row. I'm going to turn the row to become column. So this row will become 1, 2, 3. Now the next one, I'm going to turn it. I'm going to turn this to become column. So I have 2, 5, 2. And this place, I'm going to turn it. Then I will have 3, 2, 1. And notice that this matrix and this one, they are the same. Even when we turn it, they still give the same. So A now is called symmetric because its transpose is also giving itself. So that's what we call symmetric matrix. When you take the transpose and it still resembles the matrix. Alright, we'll go further to list other types of matrix. Now the next one is skew symmetric. matrix. If A denotes a matrix, and A transpose equals minus A, then A is called skew symmetric matrix. Now look at this example. I have this matrix A 2 9, then I have minus 2 minus 9 minus 5. That is matrix. I want to take a transpose, that is A transpose. We know that the transpose is, if I carry this row, I will turn it to become color. So turning it, I will have something like this 2 9. If I bring this, I'm going to turn it, so we'll have minus 2 0 5. Now I'm going to turn here. I'm going to turn here. So we have minus 9 minus 5 0. If you notice, you see that this transpose is equal to negative of A. Now notice, if I take negative of A, it will be minus times this minus, give me plus, minus times this minus, give me plus, minus times this, give me plus. Y minus times 2 will give me minus 2, minus 9 for 9, and then minus 5. So you see that the transpose give me negative of the matrix A. So matrix A will be called skew matrix. Now let us look at another one we call Hermitian matrix. Hermitian matrix. Let A be a square matrix. A is called an Hermitian matrix. If A has complex elements with the property that A is equal A bar transpose, where A bar is or denotes the conjugate of elements of A. Now see this example. If I have this matrix 1, I have 2 plus I, 3 minus 4I. I have another one here, 2 minus I, 3 plus 4i, 5, and then I have something like this: 6 minus 3i, 6 plus 3i, 2. Look at this. So I want to take the transpose of this matrix. So if I take the transpose, we know that here I will take the row, and that will give me 1, 2 plus I, then 3 minus 4i. Then this particular row, if I turn it, I will have 2 minus I, 5, 6 minus 3i. In this particular row, if I turn it, I will have 3 plus 4i, 6 plus 3i, and then 2. Now notice that at each point here, you see the conjugates. Like here, 2 plus I, you have the conjugate in the transpose. 2 minus I. 3 minus 4i, you have 3 plus 4i. 6 minus 3i, you have 6 plus 3i. So all of them give you the conjugates of it. So it means that the matrix A is called Hermitian matrix. Then the following properties hold for transpose. The following properties of transpose hold for any two square matrices A and B. With K as scalar. That is, K is scalar. Scalar means real number. So for any two matrices A and B, and K is scalar, we will have this property. Number one, that A plus B transpose will be equal A transpose plus B transpose. Number two, A transpose will be equal A. If you take the transpose of a matrix and then you take the second transpose again, you will turn back to the former matrix. That is what we are trying to say here. Okay, I. Ka transpose will be equal K A transpose IB. AB transpose will be equal B transpose times A transpose. These are the properties that will hold for any two matrices that we are taking their transpose. Alright. Now the next subtopic is algebra of matrices. We are going to look at addition. We look at subtraction. We look at multiplication. Now, addition. Addition and subtraction. So given that matrix A equal 3, 2, 1, 4, we also have matrix B to be minus 5, 2, 1, 3. Matrix C equal 8, 2, 1, and 7. We are going to find A plus B. Also find A minus C. We want to find A plus B plus C. Alright. Now look at the solution. We have that A, that is for I, A plus B will be equal 3, 2, 1, 4 plus minus 5, 2, 1, and 3. That is A plus B. And what it means is that 3 will use this element to add to this element. So we have 3 plus minus 5. Here will give us 2 plus 2. Here is 1 plus 1. And here is 4 plus 3. And this gives us minus 2, 4, 2, and 7. That is A plus B. So for I, we have A minus C. A minus C equal 3, 2, 1, 4 minus C. C is 8, 2, 1, 7. So, and that will give us 3 minus 8, 2 minus 2, 1 minus 1, then 4 minus 7. That means here we have minus 5, that is 3 minus 8 minus 5. 2 minus 2 is 0. 1 minus 1 is 0. And then here minus 3. So that is A minus C. That is A minus C, giving us this. Now, the next we have I. A plus B plus C will be equal. First, we start with the brackets. So, this will give us B plus C first, and that is minus 5, 2, 1, 3 plus C. C is 8, 2, 1, and 7. So if you add this, you will have 3, that is minus 5 plus 8. Then you have 4, 2, and 10. After getting that for B plus C, we will now start A plus B plus C. And we know that A is the matrix with element 3, 2, 1, 4 plus B plus C, which is 3, 4, 2, and 10. Now if we add this, we will have 6. 6. This will give us 3. This plus this will give us 14. So that is how we can carry out this operation. We can also do same to 3 by 3 matrix. For instance, if A, matrix A, equal 32 minus 1, 0, 4, 5, 8, 2, 1, and matrix B equal 4, 1, minus 1, 1, 1, 1, 2, 3, and 6. These are two matrices of order 3 by 3. So A plus B will be 3 plus 4. That gives you 7. 2 plus 1 minus 1 plus minus 1 gives us minus 2. So 0 plus 1 is 1. 4 plus 1 gives us 5. 5 plus 1, 6. 8 plus 2, here becomes 10. 2 plus 3 is 5. 1 plus 6 is 7. So we are able to add the matrices. Okay. Now we want to look at a very important properties that we have. That for any A, matrix A, 1 over 2 A plus A transpose, A will be equal to 1 over 2, that is half of A plus A transpose minus half of A minus A transpose. This matrix, if you have two matrices, you can divide it into two. We call one we call one symmetric and one is anti-symmetric. If you add these two, you get back the original matrix. That is what we want to show now. And let us carry out the example. We want to take the example. If A equal 3, 5, 2, and 4, find two matrices. Matrices B and C such that B is symmetric and C is anti-symmetric. So that A is equal B plus C. So we are going to find two matrices so that if you add these two matrices, it can give you back A. So solution. Now, by definition, 1 all over 2 of A plus A transpose equal B, because they say B is symmetric. And I've told you before that A will be equal half of A plus A transpose. So in this question, they say that B is symmetric and this is called symmetric. Then C will be equal 1 over 2 A minus A transpose. So these are the two matrices that if you add them, you will now get A. Right. So first thing we'll do is to find A transpose. A transpose is, look at this row, turning the row to become column. So we have 3, 5, we have 2, 4. And we want to now get A plus A transpose. A plus A transpose will then give us 3, 5, 2, 4 plus 3, 2, 5, and 4. And that will give us 6, 7, 7, and 8. This is A plus A transpose. Therefore, 1 over 2 A plus A transpose will be equal 1 over 2 of 6, 7, 7, 8. And that will give us, now, if you use this to multiply each element here, we see we will have this 6 over 2, which is 3. This one gives us 7 over 2. This one 7 over 2. And this one gives us 4 because of 8 over 2. Now, A minus A transpose will be equal 3524 minus 3254, and that will give us, you see, 3 minus 3 to give us 0, 5 minus 2 give us 3, 2 minus 5 give us minus 3, 4 minus 4 give us 0. So that 1 over 2 A minus A transpose will now become 1 over 2 of 0, 3 minus 3, 0. And that will give us 0. Now here will be minus 3 over 2. Here will be 3 over 2. And here become 0. So we are saying that matrix A will be equal to 1 over 2 A plus A transpose plus 1 over 2 S plus 1 over 2 A minus A transpose. Alright, so we then have, we know that 1 over 2 of A plus A transpose, okay, 1 over 2 of A plus A transpose is this. So we then have 3, 7 over 2, 7 over 2, 4, plus 1 over 2 A minus A transpose give us this, which is 0, 3 over 2, minus 3 over 2, and 0. Now, if we add these two, look at, we now have 3 plus 0, which is 3. Now, we have 7 over 2 plus 3 over 2. This place is 7 over 2 minus 3 over 2. And this is 4. And this will give us 3. Of course, here we have 10 over 2, which is 5. Here is 4 over 2. 4, that's 7 minus 3. 4 over 2, which is 2. Now here is 4. So notice that we have got back the matrix A by this process. And that was why we said that A equal A plus A transpose plus 1 over 2 A minus A transpose. So we are able to get it back. So given any matrix, if you need two matrices that you can add to get that one matrices, is to find a matrix where one is symmetric and one is anti-symmetric. Okay, so we'll move to next subtopic, multiplication. Now, let A equal 2, 1, 3, 4, and B is another matrix where we have minus 1, 2, 3, and minus 2. We want to look at A times B, that is matrix A times matrix B. This is 2, 1, 3, 4. Minus 1, 2, 3 minus 2. This matrix A times B. And how do we times it? This place will need attention. We times the rows by one column. So look at it. 2 times minus 1, that is 2 times this. First element times this first element. Second element times second element, that is plus 1 times 3. So I finished this first row by this column. First element times first element. Second element times second element. So we go again. 3 times minus 1, that is this row now. This element, first element, will still times this one. Plus 4 times 3. Next, we go for this particular column. You can see that these two rows, I was using it to times one particular column. So now I'm taking the two rows again to times this particular one. So I start with the first row. I will give me 2 times 2 plus 1 times minus 2. Then this one, give me 3 times 2 plus 4 times minus 2. So after that, I will now simplify it to have minus 2 plus 3 minus 3 plus 12. Then this side is 4 minus 2. Here is 6 minus 8. And that is equal, here is 1. That is minus 2 plus 3. Here is 2. Here is 9. And here is minus 2. So that is A times B. That is how we multiply matrices. Given that A equal this and B is equal to this matrix, I'm going to find A times B. Now, look at the solution. A times B will be equal 3214 minus 2, 5 times 63124 7. Now there is one thing about multiplication of matrices. Before you can multiply two matrices, the column of the first matrix must be equal to the row of the second matrix, and that is what we call conformity of matrix multiplication. Now in this, we are going to take it this way. 3 will carry each row here and times a particular column. So I will pick the first row where 3 will times 6, 2 will times 2. That is first element to first element, second element to second element. So we have 3 times 6 plus 2 times 2. We go again for the second element. 1 times 6 plus 4 times 2. Then we go again for the third row. Minus 2 times 6 plus 5 times 2. Then we'll go for this one particular column for the second matrix. We have 3 times 3 plus 2 times 4. Then we'll go again for this row. 1 times 3 plus 4 times 4. We'll go again for this row. We'll have minus 2 times 3 plus 5 times 4. Then we'll now go again each row for this particular column. That will give us 3 times 1 plus 2 times 7. Then let's go again for this row. We have first element times first element, second to second. So we have 1 times 1 plus 4 times 7. And the next one is minus 2 times 1 plus 5 times 7. So that is how we multiply two matrices. Now we are going to simplify it to have, this is 18 plus 4, this is 6 plus 8, this is minus 12 plus 10. Then in this column we have 9 plus 8, 3 plus 16. Let's see. Then here is minus 6 plus 20. Then the last column is 3 plus 14. That is 2 times 7. Then we have 1 plus 28. 7 times 4. Then we have minus 2 plus 35. 5 times 7. That gives us 22, which is 18 plus 4. And then we have again 17. The next one here is 17. Right. And 6 plus 8 it was 14. And 16 plus 3 it was 19. Then we have 29. And here we have minus 10. Then here we have 14. And we have 33. So that is A times B. That is how the matrix is multiplied, so that we get a single matrix. Alright, so let's look at another subtopic.
The next subtopic is elementary row or column operations. Now, this involves the following. 1, interchanging of one row or column to another. Also involve multiplication. Multiplication of non-zero scalar. By the row or column. Can also multiply by column. Now number 3 involves addition of multiple row. Can also be to column. Addition of multiple row to another. Here we are going to take some examples. If I have a matrix A is 1, 2, 3, 5, 9. Now I have another matrix B. Now we are saying that we can interchange one row or column to another. If I write like this, 5, 6, 9, 1, 2, 3. I have interchanged this row. I have interchanged this row to this. All right, look at another matrix C. Matrix C is 3, 3, 6, 9, and I have 5, 6, 9. Now in this one, I have multiplied row 1. I have multiplied row 1 by 3. So it gives me another matrix there, C. Okay, now see matrix D. Here, I have 1, 2, 3. I have 6, 8, 12. In that one, what I did is I've added row 1. I've added row 1 and 2 and make it to replace row 2. That's what I'm doing there. So such operations that involve interchanging of one row to another, multiplication of non-zero scalar by particular row or column, and then addition of multiples of one row to another is called row operation or elementary operations. All right, now we'll look at what we call echelon. Echelon matrix. A matrix is said to be in echelon form. Echelon form if, apart from the first row, in which A11 is not equal 0. The 0 elements preceding the non-zero elements keep on increasing, row by row. So we see a matrix is said to be in echelon form if, apart from the first row in which A11 is not equal 0, the zero elements preceding the non-zero elements keep on increasing row by row. All right, we are going to take example to understand this definition, what echelon form of a matrix is all about. Now let's take this example. Let A be this matrix. Reduce A to echelon form. Now we'll take the solution. A is the matrix 1, 2, 3, 2, 5, 7, 3, 1, 2. Now to reduce this matrix to echelon form, we have to use row operations. And so now I would like to see how I can make this place 0, make here 0, make here 0, so that the matrix will be in echelon form. Now 3 row 1 minus row 3 will replace row 3. Now this is the operation now. The operation is I'm going to use the scalar 3 to multiply row 1. Then I will minus it with row 3. You know, when 3 multiply 1, it will be 3. So that 3 minus 3 will be 0 here. So we then have 1, 2, 3, 2, 5, 7, 0. Then here, 3 times 2. So the operation there is 3 times 2 minus 1. So you have 6 minus 1, which is 5. So that 5 will replace here. Then here we have 3 times 3 minus 2. That is 3 times row 1 minus row 3. And that gives us 9 minus 2, which is 7. So we replace 7 in this place. See that? So next, we want to make here 0. And to do that, 2 times row 1 minus row 2 will replace row 2. And that will give us 1, 2, 3, 0. Then 2 times 2. 2 times 2 is 4. 4 minus 5 gives us minus 1. Then 2 times 3 is 6. 6 minus 7 it was minus 1. Then this one is 0, 5, and 7. Right, we want to reduce here to 0. And to do that, if we say 5 row 2, 5 times row 2 plus row 3, replace row 3. We'll have 1, 2, 3, 0, minus 1, minus 1, 0, and here becomes 0 because by the time 5 times here, we have minus 5. If you add them, then here becomes 0. Notice that in all the operations we are taking, the first row remain the same. When you multiply any scalar by the first row, it remain the same. You only replace the operation by the row in question. Okay, so we have 0 here. Now 5 times minus 1 is minus 5. Then if you add it to 7, you have 2. So the matrix has been reduced now to echelon form. Notice how it resembles the upper triangular matrix. So it has been reduced. Here, A has been reduced to echelon form. All right. The next one we want to look at is what we call rank. Rank of a matrix. Rank of a matrix. Let A be a matrix. The rank of A is the number of non-zero rows when the matrix is in echelon form. So that is what we call rank of a matrix. If you reduce a matrix to echelon form, the number of non-zero rows is what we call rank of the matrix. For instance, in this matrix, we have reduced it to echelon form. The number of non-zero rows here are 3. 1, 2, 3. Because here there is non-zero elements, so it means that that row is not zero all through. So the number of non-zero rows when the matrix is reduced to echelon form is what we call the rank of a matrix. Let us take an example. Now let's look at this example. Given that B equals this matrix, find the rank of B. Now let us take the solution. Matrix B equals 0, 3, minus 4, 2, minus 4, 1, minus 6, 1, 1, 2, minus 5, and 3. Now, we are going to carry out the row operation on it. Now, when you encounter this type of problems, you see the first row contains 0 here at the start. And when we define echelon matrix, we said that a matrix is said to be in echelon form if, apart from the first row, in which A11 is this first element, is not equal 0, then 0 elements preceding the first non-zero elements keep on increasing row by row. So here, because this one contains 0 at row 1 and at A11, what we'll do is to interchange it. So we can have things like this. I can say row 1 what we are saying is that row 1 will replace row 3, row 3 replace row 1. We use this sign to do that. So I will have a matrix of this form: 1, 2, minus 5, 3. Then I also have minus 4, 1, minus 6, 1, 0, 3, minus 4, and 2. So it also helped me to reduce this. It means that this place that I will have, looking for a way to make it 0, is already 0 now. So the next thing I will do is to make it 0. And the operation there will be 4 row 1 plus row 2 will replace row 2. Yes, 4 times row 1 give me 4. If I add there, here becomes 0. So I will then have another one in this form: 1, 2, minus 5, 3. Then I have 0. Now 4 times 2 is 8, plus 1 give me here 9. 4 times minus 5 is minus 20. Minus 20 plus minus 6 give me minus 26. 4 times 3 is 12, plus 1 give me 13. Then I have 0, 3, minus 4, and 2. So next I will have, I want to make here 0. So what I will do there, 3, now I will say row, yes. See, I'm going to make this one to be 0. And so 9 minus 3 row 3 can make it 0. Let us do like that. Now, and that operation will be row 2 minus 3 row 3. Now it replace row 3. See that? So if I do that, I'll then have 1, 2, minus 5, 3. Then I will also have 0, 0, 9, 9. So row 2 here, if you have here 9 minus 3, that is row 2, which is this, minus 3 row 3. So automatically this place is minus 26 as it was. So this place become 0. Now if you come here, row 2, operation there is minus 26, that is row 2, minus 3 row 3, and row 3 is minus 4. If you do that, you have minus 26 plus 12. And so what it means is that you have minus 26, 12, so you have minus 14. So we are going to replace here minus 14. If you go here, the operation is row 2 minus 3 times row 3. We'll replace row 3. So what we'll have here is row 2 is 13 in this place, minus 3 times row 3, which is 2. Whatever result you replace row 3. So here is 13 minus 6. And 13 minus 6 will give us 7. So this place becomes 7. See that? So as it is, we have reduced the matrix now to echelon form, and the rank is what? The rank is 3. How? Because this is the number of non-zero rows. Non-zero rows, we have 1, 2, 3. Most times when we reduce matrix to echelon form, this side can be 0, 0, 0. It's the way the operation will take before you know the whole place. This one is 0. Even this one can be 0, all through. If it happens in that way, then the only remaining row is the rank. Had it been that here was 0, 0, then the rank will be 2. That is only 2 rows that remain without all the elements there being 0. So that is the rank of a matrix. Now the next subtopic is application of row or column operation in solution to system of linear equations. First, we'll define system of linear equation. Now, system of linear equation is of the form a11 x1 plus a12 x2 plus a13 x3 plus we have a1n xn, which is equal b1, a21 x1 plus a22 x2 plus a23 x3 plus a2n for xn, and that gives us b2, a31 x1 plus a32 x2 plus a33 x3 a3n xn. Can continue till we have m1 x1 plus m2 x2 plus m3 x3 plus we have mn xn equal bn. Now this is system of linear equation. We can use row operation to find the solution to the system, that is to find x1 x2 x3, because x1, x2, x3, till xn, they are variables whose solutions are to be sought for. So we will do that by first what we call backward substitution. Backward substitution. In this pattern, we carry out the row operation and then keep the matrix, the system in echelon form, where we can now find the solution. Now, the practical example will help. Let us take the example. Now, let's look at this example. Solve the system of linear equation below using backward substitution. So this is the system. Let us take the solution. We have 5x minus y plus 2z equal 3. 2x plus 4y plus z equal 8. X plus 3y minus 3z equal 2. All right. So now this is line 1, line 2, and line 3. One here to be 0. That's exactly what we did during the time we used matrix. So we make here to be 0, and the operation will be line 1, or you can say row, still the same. Line 1 minus 5 line 3 will replace line 3. So if we do that, we'll have 5x minus y plus 2z equal 3. Then here is 2x plus 4y plus z equal 8. Then here is 0. But we know that line 1 minus 5 times line 3. Now look at this place. 5 times 3 is 15. So minus y minus 15y. That gives us minus 16y here. Again, here we have 2z. So 2z times 2z minus 5 times minus 3. Now see the operation here. 2, what we have there is 2, which is the coefficient of this, minus 5 times minus 3. You have 2 plus this is 15. That will give us 17z. So here is plus 17z. Now, if we go here, line 1 is 3. So 3 minus 5 times 2. 3 minus 5 times 2. You see that this is 3 minus 10. And this gives us minus 7. All right. So, next, we carry out next operation to make here 0. And to do that, we see that if we say 2 row 1 minus 5 row 2 or line 2, you know we're using line 2 line 1 minus 5 line 2 replace line 2. If you do that, we have 2 times here is 10, 5 times here is 10. So if you minus it, it becomes 0. So we have 5x minus y plus 2z equal 3. Notice that in the operation, the first rule remains the same. We know that here will become 0. Then this one is 2 line 1. The operation there for 2 line 1 means 2 times minus 1 minus 5 times 4. So this will give us minus 2 minus 20, and that is minus 22. So this place become minus 22y. We come here, the operation is 2 line 1, that is 2 times 2 minus 5 line 2. Line 2 here is 1. So we have 4 minus 5, and that gives us minus 1. So we have minus z. Go to the last one. Last one is 2 times 3. That is 2 line 1 minus 5 line 2. That is 5 times 8. Also here is 8. And we have 6 minus 40. And that gives us, 6 minus 40. So that gives us minus 34. Then line 3 is 0 minus 16y minus 17z equal minus 7. Now, row 16, another operation is 16, line 2 minus 22, line 3, replace line 3. Because we want to remove 16y to be 0, we want it to be 0. And to do that, if you multiply it by line 2 and also multiply this 22 by 16 for line 3 and replace line 3, there will be 0. So we then have 5x minus y plus 2z equal 3, 0 minus 22y minus z equal minus 34. 0, and here will become 0. Now here we have 17. We have 16 row 2. Look at that. 16 line 2. 16 times minus 1 called line 2. Here is minus 1. That is the coefficients. Okay, minus 22 line 3, which is 17. And we do that, we will have minus 16, and you have 22 times 17, which gives us minus 374. If you plus it with this, we have minus 390. That is minus 374 minus 16. Minus 390z. Then, when we go to this operation, here is minus 34. So we have 16 minus 34 minus 22 minus 7. See that? So 16 times 34. This will give us minus 544 because of the minus sign. Minus 544. Then we have another one. 22 will now times line 3. That is 22 times minus 7. That this will give us plus 154 because of the plus. Then if we have minus 544 plus 154, give us again minus 390. All right, here we have reduced the system to echelon form, and so we now start from here to see that z equal minus 390 over minus 390. You see that? So, and that becomes 1. That z is 1. We now substitute the value of z into line 2. That is, substitute z equal 1 into line 2. You have minus 22y minus then 1, because z is 1, equal minus 34. So that minus 22y, to transfer this, you have equal minus 34 plus 1. So minus 22y equal okay, this is minus. So times this become minus, cross here become plus. So adding it, we have minus 33. So it means that y will be equal minus 33 over minus 22. And this is the same as 33 over 22. And this is equivalent to 1.5. Then we now substitute z equal 1, y equal 1.5 into line 1. If you put it there, you have 5x minus y plus 2z equal 3. Will now become 5x minus 1.5, which is the value of y, plus 2 times 1 equal 3. So 5x minus 1.5 plus 2 equal 3. Now here we have that 5x. Now this is 0.5. This is plus 0.5 equal 3. No, 1.5 plus 2 give us 0.5. So 5x is 3 minus 0.5. 5x equal 2.5. X is 2.5 over 5. So that means we have the values now at x equal 2.5 over 5, y equal 1.5, and then z equal 1 are the solutions. Right. Here we may wish to check whether the solutions are correct. For instance, we have 5x as the line 1. For line 1, we have 5x minus y plus 2z equal 3. So we can now substitute this solution into the variables to see whether the left hand side can give us the right hand side. So 5 times 2.5 over 5. Of course, 2.5 over 5 is 0.5, because this will give us, if we divide this, it will give us 2.5. 0.5, yeah, 2.5 divided by 5, 0.5. So let's put 0.5 minus 1.5 in the place of y plus 2 times 1. Now 0.5, we know that 5 times 0.5 is 2.5. Then minus 1.5 plus 2. So if we add that, 2.5, look at 2.5 minus 1.5 is 1 plus 2. We see that it gives us the right hand side, which is 3. So meaning that the solutions are all correct. So that is how we can do backward substitution to get the solution of system of linear equations. All right, and let us also look at the Gaussian elimination method. The next is a Gaussian elimination method, like I've said, and we want to see how we can still solve the same system. See the same system that we use backward substitution, and we want to use Gaussian elimination method. Now the solution will be in this form. We detach the coefficients and write it in form of a matrix. 5, 2, 1, minus 1, 4, 3, 2, 1, and minus 3. This is the coefficients of the variables. Then we use dotted line to form this column, this column vector 3, 8, 2. And look at what we do there. Then by row operation, we can still carry out the row operation the same way. Here we'll see row 1 minus 5, row 3 will replace row 3. We do that operation, we'll have 5 minus 1, 2, we'll have 3, 2, 4, 1, and 8. So here becomes 0. Now here, row 1 minus 5, look at this, row 1, that is minus 1, minus 5, row 3, which is 3. If you do that, you have minus 1 minus 15, that gives us minus 16. Then here, row 1 is 2, minus 5, row 3, which is minus 3. So this was 2 plus 15, and that is 17. So we have 17 here. Now here, row 1 is 3, minus 5. Then we have row 2 to be 2. So if you do that, you have 3 minus 10. That gives us minus 7. Okay, so that is the first operation. And we want to remove these 2. And that will give us, to do that, we'll say 5. You say 2 row 1 minus 5 row 2. We'll replace row 2. If we do that, we'll have 5 minus 1, 2, 3. Then we have 0 here, because 2 times row 1 means 2 times 5 minus 5 times 2. Look at that. You have 10 minus 10, which is 0. Now if you go this, we have 2 times minus 1. That's 2 times row 1. Minus 5 times row 2. Row 2 is 4. So you have minus 2 minus 20. So that gives us minus 22. Then next one is 2 times row 1. And row 1 there is 2. Minus 5 times row 2. Row 2 is 1. And this will give us 4 minus 5, which is minus 1. So here give us minus 1. The next one is 2 times 3 minus 5 times 8. So this is 6 minus 40. That gives us minus 34. Right. So now the last row gives us 0 minus 16 plus 17 and then minus 7. So now we want to remove this one to be 0 so that the matrix can be in echelon form. When we do that, the operation will be 16 row times row 2 minus 22 row 3. We now replace row 3. So, and we'll have the matrix, the augmented matrix. You know, this matrix, when you put the dotted line and then you detach the constant, this constant value, and form a matrix. This matrix now is called augmented matrix. So the augmented matrix is minus 1 in this particular place, 2, 3. We have 0 minus 22 minus 1 minus 34, 0 here definitely will be 0. And let's all look at this operation here. The operation is 16 row 2, and that place will give us 16 minus 1 minus 22 row 3. So row 3 there is 17, and then we'll then have minus 16 minus, another one is 22 times 17, which give us 374. It was 374. Okay, so 374 plus 16, it was 390. So minus 390, we have minus 390. Okay, let us carry out the operation here. 16, that one is 16 times minus 34 minus 22 times minus 7. So 16 times 34, this gives us minus 544. This one will be plus because of this minus, and we say 22 times 7, it was 154. So 544 minus 154 will give us minus 390, and that was what we had in the other method, you see. So reaching here, can then detach the coefficients and get back the variables. So plus 2z equal 3, and here is minus 22y minus z equal minus 34, and then here is minus 390z equal minus 390. So that is how it is. And here we can then find z to be, z is equal minus 390 over minus 390. That gives us 1. Now if you substitute that into here, we then have minus 22y minus 1 equal minus 34, which means that minus 22y will be equal minus 34 plus 1. So minus 22y equal minus 33. Y is equal minus 33 over minus 22, and that gives us 33 over 22, which is 1.5 when dividing. Just exactly what we had there. Now we can substitute z equal 1, y equal 1.5 into 1 to this line 1. Line 1. If you do that, you have 5x minus 1.5 plus 2 times 1 is equal 3. So 5x minus 1.5 plus 2 equal 3. 5x plus 0.5, that is 2 minus 1.5, equal 3. It implies that 5x equal 3 minus 0.5, 5x equal 2.5. Dividing through by 5, we have that x equal 2.5 over 5. So and that gives us 0.5. So divide this. So we now have the solution that x equal 0.5, y equal 1.5, and z equal 1. So that is how we use Gaussian elimination to find solution to system of linear equation. Okay.